All right, here we are, the second half of Reynolds transport theorem and continuity, so the B section of this lecture. And we are going to focus here on solving problems using continuity. So I decided to use some of these examples that come from my. So you have this somewhere. Somewhere I've posted this on a Moodle into old homework assignments, just to kind of show you what's there. And I kind of wanted to do this a little bit because I wanted to make a point that while I like having these problems there for you to use, like for example, this one right here, number 4, consider a straight horizontal pipe, yada, yada, yada. We don't need to worry about this, okay? Because I don't want you to worry so much about these problems that are asking you to use the RTT, okay? If that made sense to you, then great. But I'm more worried about whether or not you can apply it to something a little bit more practical. Okay, so like this one right here, this is not the Reynolds transport thing, but if you read all this, this is a problem like something we did in class. And so this would be a good just if you're trying to figure out how to do a flow rate. I really like this one right here. So we're going to number 7. So we're going to go ahead and do this one. Number 7, 2 pipes are connected to an open tank of water. Pipe A and B have diameters of 8 and 10 inches. Okay, so this one has 8-inch diameter. Sometimes you'll see it written like this, phi A. Usually you'll see it as capital D. Okay, phi B equals 10 inches. Okay. Water enters the bottom of the tank from pipe A at 9 feet per second. So we've got 9 feet per second here. And the level in the tank is falling at a rate of 0.5 inches per minute. Oh, those are horrible units. Okay, so we're going to want to convert that right off the bat. In fact, let's go ahead and do that right now. So inches is going to be 12. Oh, let's do a little multiply. 12 inches to 1 foot times, let's see, minutes. We got 60 minutes to 1 hour. Not hour. Woo! We don't want to do that, do we? We want seconds. Okay, let's get out of here. Okay, it's okay to make mistakes. Okay, 1 minute is to 60 seconds, right? So now we've got, so the inches will cancel, the minutes will cancel, I'll be left with feet per second. Gives us this nasty 6.9444 feet per second. Okay, what else do we know? Assuming the tank is a cross section that is 8 feet by 12 feet. Okay, so that means the area of the tank, so that's like the area right here, if I were to draw it. Okay, so this area right here is 8 by 12, so what's that, 96 square feet. Okay, what is the velocity in pipe B? Okay, so this is all over givens. And we want to know velocity in pipe B equals what? Okay, so, well, let's think about this, shall we? Well, it seems to me that, with all of these, we're always going to solve it the same way. Okay, so I'm going to zoom way in so it doesn't take up too much space. So we can kind of stay close to our N equals out plus accumulation. Okay, what's conserved? Mass. Okay, so in, we've got one pipe in. So we're going to focus on this pipe right here. Okay, so we've got rho at A. Okay, so the density at A times the mass times the Q at A. Okay, so that's the mass flow rate in. Okay, now I could put a delta T there. Let's put a delta T there. Why not? Delta T. Okay, so let's so that's the total amount of mass flowing in over a certain time, delta T. Okay. Oh, I should probably draw my control volume. Here's my control volume. Okay, it doesn't have to go down to that pipe, but I kind of like it too. Okay, and I'm gonna actually keep it kind of below. No, let's do it the bigger way. Let's go all the way up over the top here. Okay, so we're gonna do it up there. You can do it either way. It just changes whether or not this term right here is a velocity or a what do you call it? Or a accumulation term. Okay, so now that we have that, what's out? Okay, well this is what's going out. Okay, so let's go over here, and we've got the come on, man. Okay, we've got the rho B, QB, okay, and it's flowing out over a certain time, delta T. Okay, and then the accumulation. Okay, well, the accumulation is basically going to be the change in the mass within the thing. Okay, so the mass is rho tank times the volume of the tank. Okay. So now we've got the mass flowing in equals the mass flowing out plus the accumulation. Okay, or as I always like to think about it, marbles. You know, I've got some number of marbles in here. I put in 8 marbles. I take out 3 marbles. How many have I accumulated? Well, I've accumulated plus 5 marbles. Okay, in equals out plus accumulation. Okay, but we're doing it with math now with all these crazy symbols. All right, so the first thing I want to take care of, just because it always makes me happiest, is to get rid of the rows, because so I'm going to get rid of these rows because it's incompressible. Note, it will not always be incompressible. It just so happens in this case we were dealing with water. Wait, did it say we were dealing with water? I hope we're dealing with, I know we're dealing with something incompressible. What does it say? Oh, water. Okay, cool. All right, so we're going to go down here. And now I've got Q, I don't really want to use that color. QA equals QB. Okay, notice I didn't write these delta T's because I'm going to divide everything by that. Plus change in VT, volume of the tank, over time. Okay? So now QA is UA, VA times the area of pipe A equals VB times the area of pipe B. Plus, now how do we define the volume of that tank? Well, it's going to be the area of the tank times the height of that tank divided by the height of the water in that tank. Okay, so that's change, delta T. And now we'll take the limit of this as delta T goes to 0. Okay, and so I get VA, AA equals, I'm going to take this AA and pull it outside, VB, AB plus AT, DHT, DT. Okay. So now we just need to plug in numbers. Okay. So I'll probably pause it while I do that. Okay, so if we plug in all the numbers, a few things to note. For the area of the pipes, I'm doing pi d squared on 4. Okay, for both of these, I made a point to convert them to feet. So that's 8 inches over 12 inches per foot to give me 8 over 12 feet. And then over here, remember the accumulation term is negative because we're losing mass. Okay, so if we solve this for VB, we will get VB equals 5.88 feet per second. Okay, so that's kind of how we do it. I recommend n equals out plus accumulation. It takes a little bit of thought, but these equations basically look the same every single time. Okay? You know, I mean, you can imagine a case where you have 2 pipes coming in, and if you have 2 pipes coming in, for example, then you might have a Q, let's suppose you had a C pipe that was coming in. You might have another pipe over here. You could have 2 pipes exiting, so you might have another pipe over here, QD or something. And other than that, these things pretty much always look like this. Okay, so, you know, do a little bit of thinking, and you have to build this equation from scratch, which is a little bit frustrating for you guys. It's going to be hard because you haven't done it before. All right, now I like this one as well. Number 8, air at standard conditions. I wish I could copy this. Maybe I can. No, maybe I can't copy it. Now that you cover up the stuff that's kind of annoying. Okay, and air at standard conditions enters the compressor shown below through a 2.4-inch diameter pipe. Okay, here we go. That's labeled at 10 CFS. Okay, that's labeled as well. Okay, here's slug slugs per foot cubed. Okay, so what is that? Slugs is mass. Foot cubed is volume. So that's going to be the rho. Okay. And it leaves at a velocity of 700 feet per second. 1.2 diameter pipe. And a velocity of 700 feet per second. Increased density. Okay, density is denser. Determine the average time rate of change of air in the tank. Okay, this is annoying, right? So look at this, time rate of change of air density. So air density is changing. So this is not incompressible. Because the first thing here is to figure out what it is we're solving for. Average time rate of change of air density. So time rate of change looks like this. Average time rate of change, and then air density is density of air. Okay, so that's what we're looking for. Okay, so this one's a little bit harder than the last one. All right, so what I'm going to do here is I'm going to slide over, and we're just going to think about it just like the last one. Okay, same. Come on, man. Okay, so the same equation. Okay, it's always the same equation. Okay, for anything that's conserved, you can use this equation. The beautiful thing about this, for the rest of your life, you have an energy equation. You're in thermodynamics. You're in other fluids classes. You're in some class where you have to worry about energy. You can always do this. Okay, so the N, well, mass flows into that sucker. So that's going to be, and it flows. There's only one pipe. I think it's called 1. Rho 1, Q1, that's what flows in. What flows out? Well, there's one pipe flowing out, rho 2, Q2. Okay, we'll go ahead and maybe y'all can see the pattern. Let's see. So I'm not going to put the delta T's here. Plus the accumulation. So normally I could put a little ghost delta T here and one here, but I'm not. Instead, I'm going to put it on the bottom of my accumulation. Okay, so then my accumulation is going to be d by dt. Okay, so this is where that delta t actually ends up on the bottom. Okay, I just didn't bother putting it over here on these terms and then dividing and then taking a limit. I'm just going to recognize that that's going to happen anyway. Okay, and then what's in there? Well, the change in mass. Okay, so that's going to be rho within the tank, volume within the tank. Okay, so that's just how it is. Okay, so this is how much is flowing in from the right. From the left. This is how much is leaving on the right. And this is how much is accumulating in that tank. Okay? So now we need to, let's see here. Well, all those Q's can become UAs if we want them to, but we may not want them to. And here's why. Like, look, this one right here, cubic feet per second. It's given to us as Q. This one is given to us in feet per second. So that one's a velocity. Okay, so what we want to do is we want to keep the first one as rho. So we'll call this rho 1. This is rho 2. And we're going to just go in here and let's see what we can do. Okay, so in this case, note the tank volume is constant. Okay, there's nothing changing at the volume. Okay, so let's do this one at a time. Okay, so rho 1. Well, let's just kind of let's leave it all in symbols for now. Rho 1, Q1 is left as Q1 because it's given to us like that. Okay, rho 2, we're going to leave as rho 2. And then Q2, well, we're going to change Q2 into V2A2. Okay, because they've given to us as a velocity. And then here, we're going to note that VT isn't changing. Okay, so it's going to come out, VT. And then we're left with D rho in the tank, DT. Okay, so that's what we want to know. Wait, is that what we want to know? I think that's what we want to know. Determine the time rate of change of air density within the tank. Okay, so I called it D rho air. We'll call it rho air in the tank. Okay, so let's go down here. So this is what we're solving for. Okay, we have to think about what units we're ultimately going to get out of that. And we should be getting, let's see here, rho is slugs per cubic feet. Okay, and dt is seconds. Whew, Okay, ugly units. Okay, again, I'm just gonna, at this point, all we have to do is plug stuff in. And that's what's really cool about this. I'm gonna pause it while I plug stuff in. All right, so we plug everything in, okay? And it's, it's not necessarily pretty. We've got units that we hate. We hate slugs, okay? But we've got the two rows, that's density going in and the density leaving. We've got the volumetric flow rate entering. This is the volumetric flow rate leaving, which in this case is volume 2 times area 2. Noting again that area, there's two ways you can do area. You can either do it as pi r squared, which we're most used to, or as much more often happens in this class, pi d squared over 4. So that's what I did here. We had to convert it to feet, the diameter. Okay, so 1.2 inches became 1.2 over 12 feet. And then we have the volume of the tank, and we have d rho t dt. Okay? So we do all this, and we can solve this, and I want to note something here. In this case, I put it in as a positive sign, but what's going to come out of this, it will either be positive or negative, depending basically on whether or not more coming in is leaving, or if more leaving is coming in. Okay, if this one is larger, if this side is larger than this side, then we'll have a positive thing, because there'll be more coming in than is leaving. Okay, if this side is larger than this side, then more is leaving than is coming in, so then it will be becoming less dense. Okay, so if you do the math on this, d rho t dt equals 9.1 times 10 to the negative fifths. Okay, now, excuse me, there's a 2 right here as well. Okay, so there's a temptation at this point to forget the units, because there was like a lot of junk going on. I want you to notice the units for each of these. This is slugs per second. Okay, so every second, whatever this number is, that's how many slugs are entering this thing. Okay, over here, we've got slugs per foot cubed. Okay, the foot cubed are taking care of this foot and these foot squared. Okay, and I'm left with slugs per second. Same. Okay, slugs per second. That's one thing to check while you're doing these. If the units don't work, then it doesn't work. Okay, slugs per second, slugs per second. So this is going to need to be slugs per second, right? In order to make that happen. Okay, let's see. We've got a foot squared. All right, so that's interesting. Oh, okay. So again, I didn't intentionally do this error. But notice this should be the volume of the tank. Okay, so if we go down here, this should be a foot cubed. Okay, and it turns out that, at least in this case, I didn't make an error per se. Like I didn't make a mathematical error. It didn't matter. But it could have been a mathematical error. Like I could have accidentally put an area right there instead of a volume. Okay, so with that number, now this becomes slugs per cubic foot times seconds. Okay, because notice we multiply that times foot cubed, we get slugs per second, so that they all work out. So this whole thing will be slugs per second if this is the units. Okay, so that's it. Okay. All right, so I'll do one more, and I think I will have covered kind of all the bases for this sort of madness. Okay, and this is my favorite one. I've given it on a test a couple of times. I think it's my favorite one because I made it up, as opposed to all these other ones, which, I've stolen from people who taught before who mentored me in teaching this course. And why won't you? And, whoa, we are turned all around. Okay, so anyway, and so I think I like this one because I made it up, okay? And, it's also more like the sort of things that I think about in my research. So consider the confluence of the Yellowstone River. So you can see the Yellowstone's coming in, and sure enough, it's kind of yellowish. Okay, this is the Yellowstone. And the Missouri's coming in here. Okay. As they flow downstream, /up, so this is downstream, towards the Mississippi. Sally measured the river flow in the combined river and found that the Yellowstone was carrying 13,770 CFS, and the Missouri was flowing at 4,960 CFS. Okay, exactly 1 mile downstream, so somewhere down here, I don't know where, concurrently somehow, so at the exact same moment, Sally measured the combined flow rate, so we'll say the combined flow rate, as 1,740 CFS. And let's make those Q's. So this is Q sub C, this is Q sub M, this is Q sub Y. For this 1 mile stretch, is the river rising or falling, and how fast? Okay, you may assume the river has a width of 300 feet. Okay, so it's 300 feet here, 300 feet, and this is 1 mile. Okay. Luckily for you guys, the tests are open book, open notes, so you would be able to look up that 1 mile. If you forgot, 1 mile is 5,280 feet. Okay, so this is a classic in equals out plus accumulation. Okay, there's the control volume. I just drew it. Okay, now we're basically going to assume it's rectangular. Okay, just because there's really no other way to do this. Rectangular. Okay, so what's flowing in? Well, row 1, row Yellowstone, times Q Yellowstone. That's flowing in right here. We also have this flowing in, plus row Missouri, Q Missouri. Okay, what's flowing out? Well, this combined is flowing out. Equals row combined, Q combined. Okay, what's accumulating? Plus. Okay, I don't know if it's going to be plus or minus. That's one of the things we want to know. Is the river rising or falling, and how fast? Okay, so let's see, the accumulation d by dt. Okay, because all of these are rates. Okay, d by dt of the volume. Okay, or at least the mass. Rho, I guess, what do we want to call this? Rho within this reach of the river. Rho reach. Volume reach. Okay, call that volume. All right, so let's see here. So the first thing we're going to do is we're going to note that this rho is the same everywhere, so we can pull it out of that derivative, and we can cancel it everywhere. 1, 2, 3, 4. Okay, so qy plus qm equals qc plus dvr dt. But I'm going to go ahead and make this dt. I'm going to make this the area of the reach times the depth of the reach. Okay, depth of the reach. Okay, with this area right here being this AR being the surface area, right? Because the whether or not it's going up or down, that's in the other dimension. Okay, so it seems like we got everything we need here. Okay. We should note that the area can be pulled out because it's not a function of time. Okay, it actually technically is, right? In a real river, as the river rises, usually the area increases some small amount. But in this case, we're just going to assume that we assumed that it was rectangular right here, and so we're going to assume that the banks just continue upwards. Okay, so now we just get to plug in numbers, which is pretty cool. Okay, so let's see here. Yellowstone's flowing at 13,770 CFS plus QM 4960 CFS equals QC. What is QC? Oh, 17,840 CFS. Okay, so let's see. Does that mean it's rising or falling? It looks like it's probably going to be rising. It looks like a little bit more is coming in than is leaving. Plus area, which is going to be 300 feet times 5,280 feet. Okay, times dr. Oh, that's a capital R. dt. Okay, and we just solved this sucker. Okay, so we'll say d, the change in depth with respect to time, equals 0. Oh, where's my thing? 0.00056 0.87 feet per second. Eesh. So horrible units, right? We don't really like that very much. Okay, so obviously we would prefer to use something, scientific, 5.62 times 10 to the minus 4 feet per second. And then it's kind of like, well, is that a reasonable amount? Well, if we convert that, we could say, well, d by dr dt equals 2.02 feet per hour. Okay, that seems pretty fast, right? That seems pretty fast to me. Okay, this number seems very slow, but I wouldn't expect it to rise a lot of feet per second. I mean, if you could visualize it rising per second, then you're probably in a flash flood situation. So this is, that seems pretty fast. I doubt any of you have ever seen the Mississippi River rise at this speed, although it's true I've never really paid attention to what those numbers are when the river's rising. But probably 2 feet an hour, you probably have a hurricane. Okay, so it's, that's definitely a very serious situation. All right, anyway, so these are a bunch of examples. If you search through the homework or through this, you can find more examples. I love the river example, just because it's kind of awesome. Also, I made it up, and I like it when the problems can be natural systems instead of always being, a bunch of pipes and stuff. But unfortunately, that's, the class that we're learning. So, all right, so that's it for you guys. Again, take care of yourselves. I should have your test for you later today. And as always, remember that you are more important than this class. And let me know if I can help you. All right, bye.